Hey students, this is Mr. Bornheimer, and today we are going to explore this idea of states of matter in a little bit of greater depth as we talk about transitions from one state to another. So we've already started to explore this idea, so I'm going to kind of just recap that quickly, and then we're going to take it to the next level. All right, so today's lesson is going to be on states of matter. All right, and one of the things that I really want you to be doing is I want you to be taking these notes with me because I'm gonna be talking about a lot of like key vocabulary and ideas that I know for a fact will be on your test and possibly on a quiz. And so we will be doing a lot of demonstrations and labs over the next week, and I'll be using a lot of these terms over and over again. So I really want you to be taking notes and paying attention. And if you need to pause this video, back it up, whatever, just so that you kind of it kind of helps you to understand the ideas or helps them to sink in, by all means do so. So states of matter. So let's start with the three basics, right? So we talked about this in class. We have solids, liquids, and gases. So we have these three states of matter. And one of the things that we kind of did in class is we kind of defined them, right? And I'm going to do that again in a little bit. But we also talked about the transitions from one state to another. And particularly, we talked about like solids to liquids to gases. So we kind of worked our way this way. Let's see if I can draw this easily and quickly. So we kind of worked this way, and then we worked that way. And then we did another one where we went kind of backwards that direction. So we went from gases to liquids, and then we went from liquids to solids. And that was good and all, but we never really addressed the solids to gases. Believe it or not, solids can go right to gas form, and gases can go right to solid form. And so we're going to go ahead and work those ideas in here. And so I want you, if you haven't done so already, I want you to be drawing this same diagram on your paper. So it's kind of like a triangle with 6 arrows. And there are 6 processes that we will be looking at. All right, so let's just go ahead and recap these processes. So if we're going from a solid to a liquid, okay, if we're going from a solid to a liquid, we kind of consider that like melting. That's like a fat M. We gotta break that down and make that smaller. Okay, so melting. All right, that's kind of hard for you to see, so we'll zoom in here a little bit. And then there's also, we kind of can call this like liquefying or liquefaction. For our purposes, it'll probably just be important for you to understand this idea that we can melt something that can go from solid to liquid. Okay, however, going back towards solids, we have this idea of solidification. And I like that term because it doesn't sound temperature specific. Like if we use the term freezing, we think cold, brr, like shivering, right? Well, that's not always the case, right? If you take like molten metal and you harden it, it's not really being frozen. It is, but we don't think of that as being a cold process. And so solidification is really nice because it kind of means it's becoming a solid, and that is a good term to use. Okay, then we can go down a little bit and look at this liquids to gases phase. So if we're going from liquids to gases, okay, I like to call this vaporization. gases to liquids, condensation. And last but not least, if we're going to talk about this solids to gases business, we kind of need to be talking about two terms. Okay. The first term that's really important here is sublimation. Okay, when something sublimates. Okay, and that's when it goes from being a solid to a gas. So let's write that in there. All right, the second process here is when something goes from being a gas to a solid. Oh, actually, I kind of messed that up. I wrote it with the wrong arrow. Going from a solid to a gas is sublimation, so that should have been green. And the reverse process is known as deposition. We see this process happen in terms of dry ice, right? Dry ice is CO2, and when you turn it into a solid, it becomes dry ice. Okay, that's why when you take dry ice and it's kind of smoking, it's going directly from that solid block into the gas state. It doesn't really liquefy in between. It kind of goes straight from solid to gas. Okay, so we have these different types of processes. Right, you will need to know all of them. You will need to know the direction. I would recommend knowing this chart because I think it will be very useful to you in understanding some of the things that we're going to talk about as we break these ideas down. So we have solids, liquids, and gases. And we're looking at all the different processes between these particular states of matter. Now, I need to emphasize more than anything else that all 6 of these processes are physical changes. This is a really important idea. These are not chemical reactions. The object that is going from solid, liquid to gas, etc., is not changing chemical formula. For instance, water. Water is H2O in the liquid form. Okay, so we would call this water. When it changes or freezes or solidifies, it becomes ice. But it's still H2O. If it's in the gas state, it's known as water vapor. But it's still H2O. Okay, so if something were to go from being H2O to hydrogen and oxygen, separate, it would have required a chemical reaction. If something were to go from H2O to H2O2, okay, the chemical formula changes. That would require a chemical reaction. However, if it's just changing from solid to liquid to gas or vice versa, that is not a chemical change. The chemical formula for the substance remains the same. So if lead melts and we have molten lead in the liquid form, it's still lead. That was not a chemical reaction. That was not a chemical change. This is a very important idea. Okay, so I want to emphasize that. All right, so we have solids, liquids, and gases. Now, one of the things that I told you I wanted to really look at was this idea of a molecule atom view of solids, liquids, and gases. So let's do it. Let's look at the 3. All right, so let's start with solids. In order to have a solid, okay, we need something that's got tightly packed atoms. All right, so this might look something like this. We have an atom here, and here, here. Notice that they're really close together, almost touching. And one of the things that's really important that we see here at the atomic level when it comes to atoms, okay, is this idea that because they're tightly packed together, they don't have a lot of free movement. This is an important idea. They do not have a lot of free movement. So if we take a look at these atoms, so here we are again. We had a little bit of a technical difficulty, but let's get back to it. Solids have tightly packed atoms, and so we see that here in this diagram. Right, so if we go ahead and look at these here are the atoms. And they're packed tight together. Now, that does not necessarily mean that they can't move. They're vibrating ever so slightly, but they're still moving. And so these red marks are to represent like little bits of movement. They're bumping or into each other, and they're kind of shifting back and forth in place. Okay, so there is definitely movement. However, there's not a lot of it. Okay. Also notice that these solids, when the atoms are all kind of combined together, they have edges and corners. This suggests that they have a very rigid shape. So one of the things about solids, which is really important to understand, is that they are rigid. They are rigid. They hold their shape. And the atoms vibrate in place. They're constantly shifting back and forth. One of the things that we will see which makes a difference between solids, liquids, and gases is this idea of the amount of movement of the atoms, right? So with that, let's look at liquids. Liquids, there are atoms, but they're a little bit more spread out. Notice they're not tightly packed. Okay, if we were to show their movement, we wouldn't show them as tiny little vibrating spheres. We would show them as having maybe little arrows to indicate that the movement has direction, but that it is somewhat random. Okay, this would be kind of like a liquid. A lot more movement, okay? Notice there is also no edges, no corners. So it is not rigid. It does not have a definite shape. Right? So liquids have considerably more movement than solids. okay, the atoms can slide past each other. All right, so we definitely see this in this diagram. The final model is that of the gas. And gases are really spread out. So much so that I don't really have enough room to show enough particles. And the other thing about gases is because they're more spread out, the atoms are moving much faster. Notice the arrows are much longer here to indicate that there is an increase in speed for these particles. So these particles are traveling faster. They're way more spread out. Okay, so we would say a lot of movement. A lot of movement. We would also say that that is way far apart. The particles are very spread out. Okay, so we have these ideas that solids, liquids, and gases, okay, have very different characteristics. We see them all kind of outlined here on this page. We have our solids, okay, here. We have our liquids there, and we have our gases here. Now, one of the things that we should kind of take a look at is this idea of the motion and the energy involved with that motion. So if you will recall from previous science classes, there is a type of energy that is associated with movement. Okay, we like to call it movement energy basically, but it actually has a special name. So movement has its own form of energy, okay, and it's known as kinetic energy. All right, there's this idea of kinetic energy. If we were to look at each of the solids, liquids, and gases in terms of kinetic energy, we would say that kinetic energy is present in all of them. They all have some sort of movement, but maybe for this one, the kinetic energy is small at best. Over here, we see that there is definitely an increase in kinetic energy. So compared to the solids, there's a lot more of it. And finally, for gases, there is a tremendous amount more kinetic energy per atom than there is for the other two. So we see this idea of increasing kinetic energy because there's an increasing amount of movement in the particles. More movement, more energy, more kinetic energy. Now, this obviously is all just a little bit new. Even though the ideas of atoms are kind of review, solids, liquids, and gases are new, the word kinetic energy should be in your vocabulary. But bringing it all together and looking at solids, liquids, and gases in this way is relatively new. And so one of the things that we have to kind of ask ourselves is, well, okay, if they all have little bits of different movement and the atoms are arranged differently, why is there such a wide variety of different types of particles, substances, for instance, like gasoline or oil or water, etc.? And one of the ideas that I really need to make important is that these spheres are not just atoms, okay? They are also molecules. And molecules carry with them some of their own unique properties. Okay, so I'll give you an example. H2O is a molecule with one oxygen, and then attached to that oxygen, which oftentimes is shaded red. So we'll just go ahead and shade it red for our purposes. So let's say that's an oxygen atom. And attached to that oxygen atom, oftentimes are two hydrogens. So that is where the H2O comes from. Two hydrogens and one oxygen. 3 total atoms. Now, when we're looking at different molecules, molecules are shaped and are combined with certain atoms, and they all have certain properties. So if I have a liquid that is composed of all H2O, that would be liquid water. If other things are in that liquid, maybe like an iron molecule or whatever, it will affect the outcome or how that liquid behaves. For instance, distilled water that you buy from the store is pure water, whereas water that comes out of the ground has minerals in it, and that changes the behavior of the water. Water in the ground can conduct electricity. Distilled water, which is water that has nothing else in it, can't. Okay, so there's just all kinds of there are all kinds of various properties that come with solids, liquids, and gases. We can't just say that they're just atoms. These circles could be atoms, or they could be molecules. They could be big molecules. Okay, so that's one of the things that we needed to look at. Finally, we talked a little bit about non-Newtonian solids, right? And that was the idea of like the kitchen quicksand. And one of the things that really focuses in on is when you hit kitchen quicksand, it forms a solid. But then when you let it go, it forms a liquid. And what's happening is when you hit it, it quickly forms a rigid structure like that. However, when you take the pressure off, the particles float apart and become a liquid. When you apply a stress, like punching it or hitting it, they line back up and become solid again. And when you release that stress, they begin free floating again and moving further and further apart and speeding up. And that's where the liquid portion of it comes from. So you have some substances that quickly alternate between solids and liquids, and this can happen depending on how much stress or pressure is applied to them. That is an important idea to understand. So this idea of solids, liquids, and gases plays a really important role in our understanding of weather, of pressure, of hydraulics, of all kinds of other systems that we use on a day-to-day basis. So hopefully you got a bunch of this down. Make sure that you study these 6 processes, that you understand their physical changes, not chemical, and that you understand how the atoms look and are arranged and how they behave in general for solids, liquids, and gases based on these diagrams for these notes. If you have any questions, please let me know. Otherwise, thanks for watching, and I will talk to you later.